Welcome to another session in Engineering 260, Circuits and Devices. Last time we left off, we talked about op-amps, or operational amplifiers, or op-amps for short, are ubiquitous in electronics design. They're super useful. You can do all kinds of cool applications in audio and sensors and robotics, and they're used all over the place. And so we started off by just talking about the model of an amplifier in general. And really, any amplifier has an input voltage. An amplifier is essentially a two-port device. It has an input voltage, and it provides some output voltage. There are current amplifiers, by the way, that take an input current to provide an output current, and so on and so forth, or other variations of them. But a lot of amplifiers work on transmitting signals as voltages. So that was the ideal amplifier. It's got some dependent voltage source that produces a voltage that is dependent on the input voltage. Now, any real amplifier has non-infinite input impedance or input resistance. We said we're going to be using the word impedance as we go through the course. And it has non-zero output impedance. And so what that ends up, the effect of that is that, as we discussed last time, and there are questions in the homework on this for you guys. So as you're going in to look at the homework on amplifier models and basic op amps, that's tentatively due next week. When you look at that, you'll see questions about connecting a source with some series resistance. Excuse me. And the fact that the amplifier has non-infinite input impedance, excuse me, the input stage, the amplifier is going to load down the source. Okay, and we talked about that loading. It's going to happen through a voltage divider action. Similarly, the output of the amplifier has non-zero output impedance, which means that if the unloaded output voltage, like if there's no load connected, it'll be whatever the amplifier gain of the amplifier is times the input voltage. But if you load it, then it's going to get loaded, the output gets loaded down by a voltage divider action. And so we talked about that fact. If you're looking at the total gain of the system from V out all the way to Vs, and you need to calculate that considering for loading effects, then this is the formula to use. The real gain of the system is the output voltage delivered to the load divided by, or as a ratio of the output voltage to the input voltage source, not the input to the amplifier, VI. That input to the amplifier is actually going to be less than Vs, as we talked about. So the real gain, or the total gain of the system from the voltage source all the way to the voltage delivered to the load, you need to account for loading effects at both the input by this factor, Ri over Rs plus Ri, and loading effects observed at the output by this factor, RL over Ro plus RL. Okay, that's the way you calculate the gain for the actual gain for an amplifier when you consider loading effects at the input stage and loading effects at the output stage. So keep that in mind as you would approach some of those problems in the op-amp homework on WebAssign. Okay, then we introduced the operational amplifier, and the nice thing is it condenses that this amplifier model down to a simple schematic symbol that's shown as a triangle. And you're working in the lab, these often show up as an 8-pin package, and the inputs are on certain pins. A lot of times, if it's a single op-amp package, there are pins 2 and 3, and the output is pin 6. Then there's power supply pins. Remember, it's a powered device. The current out of the output pin of the amplifier comes from the power supply lines. And that's often pin 6 on a single op-amp package. I'll just point out that some op-amp packages, if you jump over to a web search and you search, for example, an NE5532, I think, that's a, let's see, let's look at the pin out. That's a dual op-amp package. And so when you look at that op amp package, you'll notice that it actually has 2 op amps within one 8-pin package. So just all to say, not all 8-pin packages are single op amp package. In fact, there are other 8-pin packages that are completely different. They're like a small microprocessor or a piece of memory or something like that. So whenever you see an 8-pin chip on a board, you can't necessarily assume it's an op amp straight away. There are certain designs where it's a safe bet, like, oh, that's probably an op amp. And as you become more and more familiar with part names and things like that, you can you'll recognize things like an NE5532 is a classic, sort of signal and audio amplifier, dual package. Okay, so then looking at the schematic symbol, we talked about the fact that it, real op amps, any op amp has input impedance, an output impedance, RO, and a gain A. And that's the open circuit gain as a reminder. And those gain levels are very high, 100,000 to a couple hundred million. The input impedance is really high, a mega ohm up to a few, tens of tera ohms. And the output impedance is really, really low, 10 to 100 ohms. Okay, that gets close to an ideal amplifier. And so for the purposes of this course, and for a lot of circuit analysis, you can actually make the assumption that an op amp behaves like an ideal op amp. And the assumptions we make, as we stated last time, are that the gain is infinite, the input impedance is infinite, and the output impedance is 0. And from that come a few simplifications and useful models that we can use in our analysis. And that is the fact that essentially that the inputs, because if the input impedance is infinite, then the inputs don't draw any current. Pins that VN and VP, that's what we called these pins. You'll recall that we named them VN, the inverting terminal. VN is the inverting terminal or inverting input, N for negative. VP, P for positive, is the non-inverting input. Remember, we talked about if you apply a signal to this amplifier, to the non-inverting input, it'll be non-inverted at the output. If you apply a signal to the inverting input, it will be inverted at the output. We'll see examples of these amplifier types and amplifier blocks shortly. But essentially, those inputs, VN and VP, if the impedance, if this input impedance is infinite, in other words, open circuit, no current can flow into those pins. So that's one of the simplifications. And the other is that if that's true and the gain is truly infinite and you provide some feedback path, as we've talked about, this is, oops, hang on here. Let's just go from the current slide. This terminal right here, this path right here is called a feedback path. And it is, in fact, it is negative feedback because it's taking the output voltage and running it back into the negative terminal or the inverting terminal. And it turns out there's a really useful, that's a huge used, it's a widely used strategy in engineering systems in general, is the idea of negative feedback. And we'll talk about that a little bit more as we go into the course and into this section of the course. So through that feedback path, the op amp will do whatever it has to make, if the gain is truly infinite, if A is infinity, that means that VP minus VN, the difference of those, must be 0. We said, okay, the output voltage is the gain times the differential input voltage, VD. That differential input voltage, VD, is just the difference between VP and VN. And so then if you look at that gain is infinite, then the only solution is that VP minus VN must be 0. In other words, VP is equal to VN. And we refer to that as the op-amp action. So that's the big benefit here. The assumption, so again, the ideal op-amp technique allows us to say that the inputs draw zero current and that the terminals, VN and VP, will always be equal to one another. That the op-amp will do whatever it has to via this feedback path here, through that feedback path, to ensure that VN is equal to VP. And through that, we looked at our first circuit. We analyzed our first circuit and said, well, we found out that V out was equal to V1. And we called this circuit, we called it a buffer. What it does is, so this ended up providing an output voltage that was just equal to the input voltage. And we asked, what's the practical use of that? Well, it's a buffer. It isolates the source with its source resistance, R1, from the load. It prevents the load from loading down the source. And it provides that voltage right here equal to the input. It provides that with renewed current drive ability. And that current drive ability, remember, that comes from, we drew that coming from the power supply on this green line here, that if, let's say, V1 was 1 volt, then, and the load was 2 ohms, then that 1 volt is going to have to provide, the op-amp is going to have to provide 500 milliamps of current through a 2 ohm load to give you 1 volt at the output. And that's what it does. That's all it's programmed to do. And that's one of the things I want you to think of when you think of analyzing op-amp circuits. The op-amp, think of it like having a purpose or personality. Its purpose, it is a single track mind. Its only purpose in life is to source current out of the output pin or pull current into the output pin in order to make VN equal to VP. Okay. So that brings us to the golden rules of ideal op-amps. And if you follow these 2 rules, you can solve any op-amp circuit. And we're going to do that today. We're going to solve a variety of op-amp circuits today, and then arrive at the input to output relationship, or in other words, formulas for a series of common op-amp blocks. Okay, so the first rule of the first golden rule of ideal op-amps is that the inputs draw zero current. The input currents are 0. Okay, this makes our analysis way simpler. The second rule is what we call the op-amp action. The ideal op-amp will do whatever it has to force the differential voltage VD to 0. In other words, to make VN equal to VP. So that's its only purpose in life. And we're going to see how through that we can observe and we can derive, we can solve any op-amp problem, even non-standard op-amp configurations. So shortly, I'm going to introduce you to a bunch of standard op-amp configurations, namely the inverting amplifier, the non-inverting amplifier, the summing amplifier, the difference amplifier, and we've already introduced the buffer. Okay, so those are 5 that we'll go through in the next 1 or 2 sessions. All right, but before we do that, let's talk about this idea of the op-amp action. The op-amp will do whatever it has to force VD equal to 0. In other words, to make the inverting voltage, the voltage on the inverting pin, identical to the voltage on the non-inverting pin. And this is actually a concept, and it does this through negative feedback, okay, by connecting the output back to the inverting input. And this is a concept that you're actually already familiar with, even if you didn't know it yet. And one of the ways in which you are familiar with it is through temperature controllers. So, if you've used an oven, I'm sure at some point, and set it to 350 degrees Fahrenheit, and what does it do? It starts to add thermal energy into the oven until it becomes 350 degrees Fahrenheit, and it stops adding energy in once some sensor has measured that the actual temperature is 350 degrees Fahrenheit. The same thing works with a temperature controller in a room. So if you have, you know, a thermostat on a wall, let's say here is the actual room temperature. And then this point here is what we would what we can call is the desired temperature, or sometimes referred to more generally as the set point. Okay, a temperature controller is something that people study and you can design. It's a part of a broader construct called control systems. And the language in a control systems setting, and many of you will actually take courses in control systems theory, especially if you're going into mechanical or electrical engineering. You may take it if you're in computer engineering as well. If you're in civil engineering and you're taking courses in structural analysis, you won't necessarily refer to it as a control system, but you'll be talking about structural vibrations and the ways that you can tune structures to mitigate force and ground motion anomalies, or wind loading and things like that. The concepts are very similar, but in control systems courses, they refer to this thing, the desired temperature, as a set point. Now, the temperature system, then, what does it do? It's actually measuring the temperature somehow. And so what we have is, if we were to draw the analogy of what this looked like on our op-amp diagram, the load would then be like the room that we were trying to heat, if we were looking at an application of trying to heat a room. And there's some reference temperature, which this is, you know, maybe whatever, this is the reference temp of, I don't know, whatever it is. It's 0, it's ground, or whatever it is. But okay, then we have the controller itself, and that's our amplifier. Okay, now here's V out of the amplifier. The amplifier on the terminal, on the non-inverting terminal, this is VP. That is like our set point. Okay, it's our set point temperature. Now, what we're going to do is then measure the actual room temperature. So V out is like the room temp. It's measuring the room temperature. The load is the room itself, and we're going to, with feedback, we're going to measure. This is the feedback path. It could be a resistor. It could be or it could be a sensor of some kind, and that is then feeding back into the inverting input. And this is then the measured room temperature. And what's going on here? What are we trying to do? What's the control system trying to do? It's trying to make the difference between the differential voltage. We want to force that to 0. We want the measured room temperature, which is it's a measurement of the actual room temperature. We want that to become the same number as the set point temperature. So if we set it to on this diagram up here, the room temperature is set. The room temperature is 74 degrees, and it looks like this person who's pushed the down button, they're trying to cool the room. Maybe it's it looks like kind of at least in this snapshot, looks like they're trying to make the room pretty cold. They're trying to bring the temperature down to 54 degrees. Well, then what's this whole system is going to need to do? It's actually going to need to pull hot air in to the control system and then supply cool air. And so that would actually be pulling energy from the, if I was going to draw this as current here, that would be pulling energy from the load down into the negative supply rail to then cool and bring the voltage lower than it was here. So, you know, if you were drawing some voltages on here, this would be, the set point would have been 54 degrees and the measured room temperature would have been 74 degrees. We clearly need to bring the output, we need to bring that number down to bring VD equal to 0. Okay, so you're actually familiar with the idea of negative feedback and compensating for using negative feedback to compensate and bring the system into compliance. In other words, make the measured thing equal to the set point. And that's what an op amp is. It's a small little electronic control system. Okay, by the way, there are lots of other types of control systems. For example, you know, I don't know if I could find a picture of this, but in the Taipei 101 damper, let's see if we can find a picture of the damper. Oh, there it is. The Taipei 101 is a very tall structure in Taipei. And one of the neat things about it is that it uses a passive structural damping system that all it is a big mass here. Do you see this big orb that's centered it's suspended somewhere in the center of the structure. And as wind loads or earthquake loads shake the Taipei 101 building back and forth, the damping actually mitigates or brings it reduces the swaying of the building to keep it in compliance, to keep it centered toward or more vertical. That's a control system. It's not using any electronics or power systems. It's just a passive control system, but it's one in which it is keeping the structure in compliance. And that's similar to how, you know, an electronic analogy or what an op amp is doing. It's just keeping the voltage at those inputs equal. That's like keeping the structure vertical. Another application, if you take, you're going to make pasta for dinner tonight, okay? And you've got a pot with a handle on it, all right? And then you go to the sink, and let's say I don't know, the bottom of your sink is full of dishes or something. You can't rest the pot in the sink. You're going to turn on the water, and what happens as more and more water comes into the pot gets heavier. So then you, as compensating with your arm, you have to provide more and more leverage as there's more and more water in there. Your arm is then acting as a control system, holding the pot level. You're keeping it at a vertical or a horizontal state while it's becoming more and more heavy. And so your arm, and you know, you're sensing it, you're measuring it by a tactile feel of how heavy it is and how much it's pulling on you. But your, you know, biological arm and measurement system is providing a control system that's keeping that pot level. And an op amp is an electronic version of that. Okay, so let's now derive the circuit response and the behavior of a number of very common op amp blocks. And as I mentioned, we just introduced the follower. We'll revisit that really quickly here. Then we're going to look at the inverting amplifier. Then we're going to look briefly at just a non-standard op amp block. Then we're going to look at a non-inverting amplifier. Then we'll look at a summing amplifier, and if we have time, we'll start to look at a difference amplifier, but I expect we'll probably get to the summing amplifier today. All right. So let's revisit the voltage follower. We just looked at this here. So if this is Vs here, remember that there is zero current going into either of these inputs. And so, so then this voltage here is also Vs, which makes, by the op amp action, this is Vs, which makes the output equal to Vs. So anytime you see an op amp block like this, so this now when you're viewing circuit schematics, right? and you see something like this, where there is a feedback path, RF is 0 ohms. In other words, the output is connected directly back to the inverting terminal via a short circuit. That tells you that this is a voltage follower or a buffer. And anytime you see a voltage follower or buffer, you know that the output voltage is just equal to whatever the input voltage is, even if the input voltage is connected through some resistor here, like this. All right. You don't always see that, by the way. Sometimes you may see something that looks just like this. Here's VS connected through an op amp to the non-inverting terminal. The inverting terminal is connected there, and here's V out. Sometimes you just see it like that. That's also that if you recognize that op amp block, that is also a buffer. Okay. You know, the other time when we met, we pulled up this schematic of the Watt compressor, and D. Thomas here. Let's see. Oops, misspelled this. And we looked at the schematic here. I wonder if we could actually see any if we could see any buffers or voltage followers in the schematic. I kind of forget if there is one, honestly. Oh, it looks like he kind of changed this since the last time I looked at it, but you know, not quite. There is something really close to a buffer in here, and it's this point right here, U3 with this diode in there. You see how the signal is fed into the non-inverting terminal. The output is connected back to the inverting terminal on pin 2. It's almost connected directly, except there's a diode in the path. That is almost a buffer. It's actually a rectifying buffer, but at any rate, what I'm mentioning here, the reason I pull this up is so that you can start to see common op amp blocks. When you stick a diode in there, that does do another action. It's a rectifying follower, but we can see circuits where you'll start to see those in examples there. All right, let's then move on and look at the next common op amp block, the basic inverting amplifier. Okay, so how do you recognize an inverting amplifier? You recognize an inverting amplifier when VI, the input voltage, is connected to the inverting terminal, VN. Okay, remember VN is the one with the minus sign on it there. Okay, so let's then, what we're going to do is to derive how this thing works and what the formula is. We're going to do two things. We're going to go through the ideal op amp techniques. So we're going to employ the ideal op amp techniques. And two things I want you to take away are the ideal op amp rules. You know what? Let's just actually call them the golden op amp rules. One is that IN, the current into the inverting terminal, which is shown here, is equal to IP, the current into the non-inverting terminal, are both equal to 0, right? There's no current into the inputs. The second op amp rule, the golden rule, is that VN, that the op amp will do whatever it has to make VN equal to VP. How is it going to do that? Well, realize that this voltage right here, this is VN, right? And this voltage at this point is VP. The op amp will either push current into VN, or it will pull current away from VN so that VN either goes up or down in voltage accordingly to make it equal to VP. And it's doing that through the feedback resistance. Okay, that's the thing. Is if you can just feel comfortable with that the op amp is this, it is this small little entity. The triangle looks confusing because it looks different than anything we've done in circuits so far. But if you can feel comfortable with the fact that it actually is powered from a power supply source, I'm going to draw those in purple here. So we have a plus VS and we've got a minus VS. Remember, most of the time those aren't drawn. Just for clarity, for simplicity's sake, but that's where the current is either coming from or going to. All right, and the op amp will do whatever it has to make VN equal to VP. So let's then go ahead and do nodal analysis at V1. All right, so V1 is shown here. V2 is shown there. V1 is equal to VP. Oh, I'm sorry, V1 is equal to VN and V2 is equal to VP. We're going to use the numbering system that they have here on the slide. All right. So let's do nodal analysis at V1. Okay, so if we do nodal analysis at V1, we really have two currents going into and out of V1. There's the current I1 going from the source VI through R1, and then there's the current I2, and that's it. Remember that IN is, there's 0 amps going into the inverting terminal, and the same for VP. Okay. So, so if we do nodal analysis there, then we have VI minus V1 over R1. We're doing far minus near, right? Plus V out minus V1 over RF. That's the other, that's, here's V out, right? And then, so the current going through RF from V out to V1 is that this term right here, V out minus V1 over RF. And that's all the currents in and out of the node at V1. So that is all equal to 0. Now, we've just invoked op amp, golden op amp rule number 1, right? We invoked that. We said the currents in and out of those pins are 0. So it made setting up a node equation, a nodal analysis equation at V1 really simple. Now we're going to invoke op amp rule number 2, because if you check it out, VP is equal to 0 volts because it's grounded, right? It's grounded. So by the op amp action, V1 equals 0 volts by the op amp rule number 2, the golden op amp rule number 2. It is also equal to 0 volts. So what that allows us to do is then set this to 0 in both of these terms. V1 is equal to 0. And what we end up with is that VI over R1 is equal to a negative V out over RF, right? If we move that this V out over RF term over to the other side. And what that then means is that V out, the output voltage, because that's what we're trying to do here, by the way. Every single time we're trying to, when we are deriving the relationship or the formulas for these common op amp blocks, we want to find out what V out is as a function of VI. That's what we're looking for. So V out as a function of VI is equal to negative RF over R1 times VI. And that is the formula. So let's see, let's draw up a couple of things on here. Notice the fact that it is inverted. The gain is negative. So if VI is positive 1 volt, V out is going to be a negative value. And let's also note the fact that the gain G is equal to RF. Hang on here, let me write that in a clearer spot. The gain G is equal to RF over R1. Okay, so you can set that gain. When that means, so what are the values for the gain? What are the possible values for the gain? The gain could be, well, what could we do? We could make RF equal to 0. If RF is 0, then the gain is 0. And or we could make the R1, we could make that 0, and the gain is then infinite, or RF could be infinity. And now that's just theoretically. Of course, the op amp won't be able to infinitely amplify the signal. So let's talk about feeding, as you start to work with amplifiers, what's really useful is to look at how they behave with AC signals. So let's say that we take a graph. Let's plot a graph of the input voltage versus or voltage versus time. So let's say this is a graph of V versus T, and we apply a sine wave input on here. Okay, and let's say, so this is VI right here. Let's say that you apply a gain that's bigger than 1. Oh, and by the way, also, like if this were, let's say that this was 1 volt, plus 1 volt and minus 1 volt, we would say that this signal, by the way, is 2 volts peak to peak, because the peak to peak voltage is a total of 2 volts. All right, I want to introduce you to that terminology. You're going to work in the homework, and let's see if we're back over to the homework here. If I go and view the amplifier homework, you'll see that some of these, so sometimes people write it peak peak, like PK dash PK. Sometimes people write it as VPP. That's kind of pretty common, VPP. So they say a function generator whose output resistance is 215 ohms is adjusted to produce an open circuit sinusoidal output voltage of 0.6 volts peak to peak. That's terminology I want you to be familiar with. All right. Okay. So peak to peak means the peak to peak voltage. So to use the same terminology, I'll just write it here to VPP. All right. So if, let's say we were to produce let's say we wired up this op amp with a gain, we chose the resistors RF and R1 such that we got a gain bigger than 1. The output signal would look like this. Something like this anyways. No, I didn't do a great job of drawing that. Something like this. This would be a gain. This would be V out with a gain greater than 1. Now, the gain doesn't have to be bigger than 1. The gain could be less than 1. which is a useful characteristic of this op-amp type, by the way. Not all op-amp structures are actually can give you a gain of less than 1. So if there were a gain of less than 1, it's still inverted, but the signal is now smaller. And so this would be V out with a gain less than 1. Okay, and let me just try to draw my -1 volt line a little clearer here, something like that. Okay, let's talk a little bit about current flow in this circuit. So if you have current flowing through R1, none of it can go into VN, so the current has to go through RF, and then it's coming into the input here or to the output pin V out. And where does it go from there? Well, it's got to go down to -Vs. That's how the current flow works in this circuit. Not everybody would actually cover this in a circuits class. Sometimes I see it sort of overlooked, so to speak. I want you to remember that the op-amp, and it's not always easily seen because the power supply lines aren't always drawn, but the op-amp is powered with pins +Vs and -Vs. And when current can either go out of, you can source current out of the output pin, or you can sink current in to the output pin. And it'll either, if you're sinking current, it'll go down to -Vs. If you're sourcing current, it comes from Vs, from positive Vs. Now, if you take a look at it, take a look at the red line here on V out. At this point here, if V out is negative, that means that the device is sinking current, right? This would be like +1 volt here, and we're going to get, let's say, a -1 volt there. When that's happening, this is sinking current. All right. When V out is positive, that's sourcing current. This is going to come from +Vs, and this is going to -Vs, the supply voltage. And Jeff writes in, does that cause a problem for the power supply? Great question. Not as long as you're within the limitations of the op-amp. Let's actually go and jump over to take a look at the characteristics of the op-amp you guys are working with in lab. I believe it's the LM741. And where you can find those characteristics for any electronic component is in the data sheet. Now, many companies make an LM741. Let's look at the Texas Instruments data sheet here. And if you take a look at it, I think this is not quite what we want. Let's look at this here. Okay, so here's the LM741 operational amplifier. The data sheet tells you not everything you need to know, but lots of things you need to know about the op-amp, about any electronic component. If you're working with a sensor or, various kinds of capacitors or, other kinds of amplifiers or microcontrollers or shift registers, memory, all kinds of things, okay? So it tells you some applications. These are good for summing amplifiers. That's something we're gonna look at. We're gonna look at a summing amplifier application. Integrators or differentiators, active filters. We'll get to filters later on in this course. DC amplifiers, so amplifying DC voltages, not AC voltages. And comparators and multivibrators are special kinds of amplifier circuits. So here's the pinout, okay? And if we go and look at the specifications here, absolute maximum ratings, ESD ratings, ESD stands for electrostatic discharge, thermal information and yada, yada. Let's go and click there. Here we go. So take a look. The LM741, the supply, here's some stuff for the supply voltage. The maximum for the 741 and the 741A, the maximum supply voltage values. So these in purple, plus VS and minus VS, the most that you can power it with is plus and minus 22 volts respectively at each pin. So VS could be 22 volts, negative VS could be, the minus VS terminal could be minus 22 volts. And nothing more. If you apply any more, it can fry the amplifier. So now let's look at the interesting. Let's see. ESD ratings, electrostatic discharge. Here we go. Input offset current, input bias current, and here it is. The output short circuit current. The maximum short circuit current, the maximum current that the LM741 op amp is able to produce is 25 milliamps out of the pins. There are reasons for that. It's a little 8-pin package. It is made on a silicon die. Currents at levels greater than that start to heat up the internal components to a point where there's enough thermal energy that parts start to fail. Components start to fail. So the answer to your question is yes, it can stress the power supply. If you had a power supply that could only produce 10 milliamps of current, and the 741 is trying to produce, let's say, up to 20 milliamps of current within its spec, then yes, that's going to strain the power supply. Now, most power supplies can power well above 10 milliamps of current. And so typically, the constraint would be within the part itself, within the op amp itself, and you might need a higher current operating amplifier. So then you can go and look for something like this, a high current output op amp, and look around and see what you find. Here's a from DigiKey, an LT linear technology 6274, something or other. If we go and look at the feature set, it looks like it has, let's see, are we finding it? Well, I don't see it listed here very clearly. It might possibly be that it's not showing that spec really clearly here, and maybe I found the wrong part or something like that. But I think this is actually a low power. Yeah, so you might want to go and, yeah, oh, here's over 100 milliamps, right? So here's some output currents, amplifiers that have currents over 100 milliamps. So great question. That's something I want you guys to think about. Questions like that are allow you to make the bridge, the jump from analyzing op amps on paper with ideal op amp techniques, but realizing that when you go to design something, you're going to use a real part that is going to have real limitations. And so on paper, we could design something that, you know, an op amp is, I don't know, supplying 10 amps of current to some load. And that's not realistic. So if you actually wanted to provide 10 amps of current with a load, you would use an op amp in conjunction with some other kind of amplifying device like a transistor. Now, Carl writes in, you mentioned that precise resistors cost more. What would make an op amp more expensive? So similar kinds of constraints. Op amps, when they're high precision, they like tuning things in components inside of the op amp makes them more expensive. So low noise, high current output. There's a lot of ways that you can tune an amplifier. You can make it high speed, so it works on really high frequency signals. Like it can amplify a sine wave or a square wave faithfully up to, let's say, a few hundred megahertz or a few hundred gigahertz. To design an amplifier that is able to do that, you have to make certain specifications. The designer, the op-amp designer, Texas Instruments or Linear Technology or Analog Devices, which the last two companies are now the same, Analog bought Linear Technology. But to design those things, you actually have to make adjustments in that case, it's often the input stage and the output stages. But in doing so, if you make it really high speed, you're always adjusting. Something you're adjusting there is going to make it less, it will work less well for other applications like low power, for example. So the higher speed op-amp that you design it, it's going to be less of a low power op-amp, one that just does not really consume much standby power when it's not operational, when it's not running and doing its job. So those are the kinds of things that can make amplifiers expensive. To give you an idea of some of the prices, the LM741 is really cheap in low quantity. If we just look at low quantity numbers, anything as you scale it, if you buy 100,000 of them, the price goes way down. But just in terms of low quantity, quantity one, the LM741 I think is 50 cents. Now quantity one of an analog device is 797, I think that's it, 797. That's an ultra low noise amplifier used commonly in audio applications. Those are $10 each. So it gives you an idea. There's a range right there. There are more expensive and less expensive amplifiers, but that gives you an idea of some of the ranges that these things can cost. Again, in low quantity. Okay, so let's then go and look at an arbitrary circuit. Here's one. So when we see, so getting back to this, when you see a source connected to an op-amp where the inverting terminal, the non-inverting terminal is grounded, and the inverting terminal, the signal is applied through a resistor to the inverting terminal, and there's one feedback resistor, that's an inverting amplifier. And so if we went back to our schematic that we were looking at on this compressor, remember I said I built one of these. In fact, I've built a few of them. It's a nice design, actually. But take a look at the input stage. Look at this. Remember I talked about this last time. Here's the left signal input, and it's coming in through jack 1. It comes through a 100K resistor, and then notice this. It then is connected to the inverting terminal of this op-amp, U1A. The non-inverting terminal, pin 3, is tied to ground. And there's a feedback resistor. There's a resistor in the feedback path connecting the output back to the inverting input, also a value 100K. Haha, what's the gain of this stage? The gain of this stage, whoops. Remember, the gain is RF over R1. So the feedback resistor is 100K. R1, which is also coincidentally labeled R1 in this schematic because it's the first part, is 100K. That means the gain of the two of these things with this op-amp is 100K over 100K. It's a gain of 1. But remember that it's an inverting op-amp, so it's a gain of -1. What's the purpose of this block right here? All it does is it isolates. The designer is using this as a buffer, essentially, with a gain of 1 to also invert the signal. You'll recall that the buffer we looked at last time does not invert the signal. V out is equal to whatever the signal voltage is. So in this case, it seems like the designer wanted to isolate or buffer the signal from, it comes from the outside world connected to, you don't know what happens in the outside world. The cables could be, you design a product and some user connects whatever cables to it and runs them wherever they do. That cable could be wired up in a coil stuck next to highly inductive load like a motor on a AC unit or something like that, cooling a house. That's not the best idea. Or it could be stuck next to, or maybe you're near a radio tower. So a student of mine once was building a project, but he lived right next to Sutro Tower on the top of Twin Peaks in San Francisco. And so he was trying to design an audio amplifier, and he was getting all kinds of radio frequency interference. So you never know what happens out in the outside world. So people go to great lengths to design input stages that help to start to tame any of the problems that could come up in the outside world. And one of the things this designer did, it looks like here, has just done a 100K input impedance. So that's helping not load down whatever the source impedance is. And then he's implemented an inverting amplifier here to buffer the input. All right. So that allows you to now recognize this as, so when you zoom out, this whole thing looks super complicated, right? If you take it in sum total, it looks like, how do you even possibly follow through what this is doing? The technique that you're now learning is to identify common circuit blocks. So when you see a voltage divider, that can help you identify common things. I don't know if there is a voltage divider in here anywhere. Don't really see one. Here's a potentiometer. That's pretty common, but don't see one in here exactly. But we're going to talk about RC circuits soon, right? RC circuits. Here's a couple of resistors with a capacitor tied to ground. This thing right here forms an RC circuit. As you saw in physics, when it's a time constant, an exponentially charged, an exponential discharge, that's a sub-circuit, a sub-block. So as you're going through these, you're going to be able to recognize more and more common op-amp blocks, okay, and common circuit blocks, and it allows you to analyze really big circuits and break them into smaller pieces. It also allows you to design circuits by connecting, cascading various sub-blocks. So this is an inverting amplifier. This is going through a potentiometer that then goes through another stage. And we'll talk about what this stage does when we learn more of these op-amp blocks. So let's do that. In fact, why don't we, before we do this, you know what, let's go ahead and do the basic, instead of coming to this circuit here, which is not an inverting amplifier, it's not a non-inverting amplifier, we would need to apply the golden op-amp rules. You know what I decided I wanted to do? Let's do the non-inverting amplifier now. Okay, so how do you recognize a non-inverting amplifier? The non-inverting amplifier is the source. The source is connected to VP. That's how you recognize a non-inverting amplifier. Now, just one thing to think of, even if there's a resistor connected between VP here and the source, V source. So this is VI, the source, right? Even if there's a resistor connected between those things, remember that at least for ideal op amps, there's zero current going into there. And so VP would still equal VI, and this would still be a non-inverting amplifier. That's something to keep in mind. Sometimes people do put a little bit of source in, a little bit of resistance in series feeding into the inverting terminal or non-inverting terminal. And that's just done for various design constraints or accommodations. So let's then analyze, let's derive the relationship for this common op-amp block. And we'll do it using the golden op-amp, OA for short, rules. Okay, remember number one is that IN is equal to IP is equal to 0. The input pins draw 0 current. And number two, that the op-amp will do whatever it has to, whatever is necessary to force VN equal to VP. All right, so then by rule number one, we can do a nodal analysis at Vn. Okay, so by rule one, there's 0 current going into either of these inputs. And so if we do nodal analysis at V1, we just have the current going through here and the current going through R1 and the current going through RF. So we'll do far minus near. and we'll set it up. So we've got a 0, this current going through R1, we've got a 0 minus Vn over R1 plus a, here we're doing far minus near, this is V out. So the current going through RF, which if we were going to draw it on there, like far minus near is going this way, even though it may or may not be going that way, is a V out minus Vn over RF, the feedback resistor. Okay, that takes care of all the currents through there, and so that's 0. All right, now let's go ahead and invoke rule number 2. If this is Vi, then the op amp will do whatever it has to make Vn equal to Vi. So by rule number 2, we have that Vn is equal to Vi. And voila, at this stage, we now have a single formula where it has V out terms in it and VI terms in it. So let's then go and write this in terms of those things. So if I pull the V out over RF term, if I leave that over on the left side of the equation, and then on the right side of the equation, I'm going to group the VIs together. And you'll notice that if we moved this term over to the right and this term over to the right, they're both going to become positive, right? I meant to draw this as having that negative in there, right? Both of those are going to become positive. It's a 1 over R1 plus a 1 over RF when they moved over to the other side. All right. Now, if we multiply both sides of the expression by RF, we get that V out is equal to, let me just do that again here. V out is equal to VI times, I'm going to factor this in here just like this, RF over R1 plus RF over RF, right? Which that last term is a 1. RF over RF. So we'll write it as in standard form. This is V out, hang on here. V out is equal to VI times 1 plus RF over R1. That is the formula for a non-inverting amplifier. So whenever you see an amplifier that looks this way, oftentimes notice too that R1, the other resistor, this is tied down to ground. So when you see it like that, and sometimes, you know, it might look more like this. You might see something like, here's VI, here's the source, and then you've got something like, this would be V out, here's R1, here's RF, and R1 would just be grounded like that. Sometimes you'll see it that way. That's a non-inverting amplifier as well. Okay, it's just drawn a little differently. It's the same thing as what's on the schematic here, just drawn a little bit more shorthand. So let's talk about the fact that the gain is non-inverted. There's no negative sign there, and we can see the fact that this is the gain. The gain G is anything between 1 and infinity. And again, that's theoretically. If we were to draw what this looked like on here, if we were drawing a graph of V versus time, whoops, and we drew VI, and we could draw then in a gain of, it's going to be a gain of greater than 1. looks something like this. I did not draw a very great sine wave right there, but that's basically what's going on. So this is V out with a gain of greater than 1. You can't have a gain less than 1 in this kind of op amp. So we've now just introduced the non-inverting amplifier. And if we go back to that schematic, take a look at this. What does this look like? So if I come over here, and we just looked at this block here, right? That was an inverting amplifier with a gain of 1. Now, if we come over here, take a look at this. Okay, so what happens then? The output then is fed through some potentiometer. We haven't looked at potentiometers a whole lot yet. We will shortly, but essentially they're just a variable resistor kind of voltage divider thing, where the voltage on this pin can be adjusted to anywhere between the full voltage coming out of that amplifier or ground. It's essentially a dial, like a volume knob on a piece of audio equipment. If you adjust it and you turn it up, you can hear more of the signal. That's exactly what's going on in this particular application. And if we look further, where does it then go into? It goes into this amplifier block. Take a look at that. That there is, what is it? It's going into, the signal is going into the inverting terminal. The negative terminal is the inverting terminal. There's a feedback resistor going from the output of 10K, from the output back to 10K. There's a resistor tied down to ground. That's like the other resistor. This is a 1K, 1 kilo ohm resistor. And so that block there, that's an inverting amplifier with a gain of, the gain is 1 plus 10K over 1K, or a gain of 11 volts per volt. So what we're able to do now is start to trace through what's happening with the signal, and we can just look at it piece by piece here. All right, so next time, now that we've derived the equations for the follower or the buffer, the inverting amplifier, the non-inverting amplifier, and we've derived the gain relationships for those, the V out to VI relationships. So anytime you see one of those blocks, those common blocks, you can use the equations that we've derived here. You don't need to rederive them from the basic op-amp rules and circuit analysis techniques like nodal analysis. When we come back next time, we'll look at a non-standard circuit. This particular circuit is neither an inverting amplifier, nor is it a non-inverting amplifier. And so you can't use either the this formula to get the output voltage. You can't use the non-inverting formula to get the output voltage. But instead, we have to analyze it from scratch using the golden op-amp rules. And that's true anytime you see a non-inverting terminal. Jeff writes, I thought the non-inverting terminal was positive. The non-inverting terminal is positive. Did I write something? Was it when I was on the schematic? Yeah, so this guy here, that's a non-inverting terminal. That's positive. So this is if I wrote inverting up there, I meant to write non-inverting. Sorry. But you're right, Jeff. The inverting terminal is positive.
Okay, yeah, I thought you were referring to that as an inverting.
Sorry, yeah,
but it's.
Yeah, I think I just mixed up my word. It's non-inverting. So we'll do this particular problem here and derive it from basic principles. And then next time we'll also look at a summing amplifier and then I'll get you some. We'll take a look at some applications, and I'll probably post some videos that go through a difference amplifier and some applications there. So I look forward to continuing this segment with you. This is certainly an exciting topic in the course. I know it feels a little bit weird because the triangle looks different than the rest of the schematic stuff we've been doing so far, but trust me, as you follow the golden op-amp rules and start to recognize op-amp blocks, this stuff will get easier. So thanks for tuning in. Look forward to see you next time, and until then.